Start recording.
Great. All right, so welcome to lecture 13. Today we're gonna talk a little more about LQR just at the start, to show how we can extend it to nonlinear systems. And then we'll touch on a class of methods called sampling-based MPC. And then we'll study this idea called Lyapunov theory, right? And that'll be kind of our outline for today. Where we are in the class is we've talked about feedback control. We've instantiated feedback control with PID control and bang bang. And we started talking about LQR. We worked out the LQR recursive equations. And today we're going to kind of complement LQR with MPC and study how we can make these controllers safe through the Lyapunov theory. So some logistics before we get started. Homework 3 should be out now. It was due originally on the 12th, but we pushed it back by 2 days to the 14th. It's easier than homework 2, but still start early. Things on the car take time, and you have to actually drive the car around with an autonomous thing. And so try to do that early. We're going to have paper readings this Wednesday. I sent out emails to both the groups and posted on EdStat. But I think the groups are E3 and Dashbot. But those are the papers we're going to read. You can look them up. They're related. Yeah.
When do we do the question?
Oh, like next Monday. We're gonna go. Yeah, we'll go relatively slow then. Okay. Any other logistics questions about homework 2 or anything else that we need to sort out? Anything you wish was different about homework 2? Okay, well, send me an email if there's something you would like to change. We can try changing it. But today's structure is we're going to do a little recap of LQR, and then study this idea for competitive LQR. And we'll study sampling-based optimal control, and lastly, we'll talk about Lyapunov stability. Okay. That's going to be our structure. So to recap our general optimal control problem, instead of just the problem of stabilizing to a particular state, the optimal control problem tries to find a series of actions you want to keep, such that when you act according to those in your system F, you minimize the cost. Right? And so you can incorporate things like, preferences, and you can incorporate staying away from obstacles and smoothness and other things like that into your cost, and try to optimize this optimal control problem in a variety of ways, one of which is LQR. Right? So to kind of recap what LQR is an optimal control problem where the dynamics F are linear and the cost function C is quadratic. And so the general LQR system looks something like this. Right. And so what we did last class, just to recap, does everyone remember what we did last class? Okay, so we won't rederive it, but basically the LQR system, we try to solve this particular series of equations. So we try to solve this minimization problem with this series of equations, right? And we do it with dynamic programming. So we started from the last time step. We worked out that the controls of the last time step were 0. Then we went to the second last time step. We worked out the controls at the second last time step, and we made a recursion out of it, right? And so we ended up with a system that looks something like this, right? And in this system, you have your controller at any time step is linear in the state, and your cost to go is quadratic in the state, right? And you can get these KIs and PIs through this recursive equation. So the last time step, your KIs or your PI is going to be Q, right? And your action is going to be 0. That's your base case. And then every step before that, you're just going to go backwards. And you're going to like iteratively use this equation for KI and this equation for PI. And so KI is your gain, PI is your cost to go coefficient, right? So you can think of JI as your cost to go when you have I steps left. And KI is your gain that tells you how to get a controller from your current state. Does that ring a bell for everyone? Any questions? So just to recap what these mean intuitively, right? The gain you can think of as something that trades off. Let me just write this out. The gain here is something that's trading off these two terms, B transpose PA by B transpose PB plus R, right? And so you can think of this thingy as essentially trading off R and B So P is the future cost, R is the current cost, and you can think of the gain as something that trades off the current and future cost, right? And so it's kind of the same thing as Kalman filtering. And then the cost to go is just like plugging in the gain into the cost equation. So this is your current state cost, your current action cost, and your future cost, right? And so that's the intuitive way to think about it. It's like current state, current action, future. This is a term that trades off between the current and the future and tells you how to take control. So if, for instance, R was extremely high, then you would immediately set your actions to 0. And if R was extremely small, then you would try to set your actions so that your state goes to 0, right? So those are the ways to think about this intuitively. Does that make sense? We're kind of parsing. Okay, so okay, so that's the general intuition behind LQR. And we won't recap LQR too deeply, but the general LQR algorithm, you can implement something like this. Your base case is gain 0, cost to go Q, and then every step after that, you're going to just repeat this recursive equation for Ki and E, right? And that's going to give you your controllers and your cost to go at every step. Once you have these controllers, you can just run your feedback controller. You don't have to recompute anything. You just run your feedback controller with Ki at every time step, right? So you compute a bunch of Ki's from K0 to Kp, and then you try to like play your controllers according to like if you're at time step 0, you play some K. If you're at time step 1, you play another K. Okay, so that's the idea behind LQR. Now, what's the issue with it? Has it solved AGI? What's the problem?
What is it now slow to compute if something changes?
It can be slow to compute. Yeah. If something changes, so that's definitely an issue. Well, I had to run that earlier, but it's a bit slow. But I think it's relatively less slow than something like reinforcement learning, right? So the main issue with LQR is that it's linear and quadratic, right? And so the world is not linear or quadratic. And so that often causes your problems. And so we're going to try and see an extension that makes it applicable to nonlinear systems. But before that, some videos of LQR. This one's from my PhD advisor, Peter, that is using LQR on this like Stanford autonomous helicopter. And they try to do like acrobatics with this helicopter. Which I thought was pretty cool. And it just uses a version of iterative LQR plus some magic sauce.
Right.
Yeah. Yeah, I think he's done it pretty well. But yeah, for those of you who are interested in helicopter dynamics, I think they do a good job. And the nice thing about it is like they're not doing explicit modeling of all the wind conditions and everything. A lot of that is coming from feedback control and iterative linearization.
That's just by adding noise.
Yeah. By adding noise and that. Okay.
What is assuming it's scanning its surroundings, know where it's at?
No, it's in free space right now. So yeah, that's
What, is it just scanning of where the ground is basically?
Yeah.
Make sure there's
And-
no like trees around
yeah,
it?
exactly.
Kind of
Yeah,
all-
that's about it.
It's like
It's like maybe like that big, it's like a toyish helicopter, yeah. It's like one of those hobby helicopters. If you put a human in there, they would probably die. Or throw up. And you can also use this for other types of locomotion systems. So this is another one from Clem, where they're trying to do like this two-wheel robot navigating around different ramps and so on. Similarly, using whole body, like a LQR for whole body control. So you should read these papers. I think they have nice demonstrations. But you can see here that when you introduce disturbances, because it's a feedback controller, you can recover. And so it's not like widely susceptible to disturbances like an open loop control. Cool. Okay, so the issue with LQR is that the world is neither linear, which should be flipped, but the world is neither linear nor quadratic, right? And so we want to deal with nonlinear, non-quadratic systems. So the trick is just to use Taylor expansion, right? So here, what does the Taylor expansion say? It says that if you have a function, you can write it as, a sum of each of these terms, which are different polynomials, right? So you have f of x, you can write as f of a plus f derivative evaluated in A times X minus A, and so on and so forth, right? And so you can choose the level of approximation that you want. So first order Taylor approximation is going to try and say, just choose the first two terms, and then the second order Taylor approximation will choose the first three terms. Right? But the important bit is that the Taylor approximation lets you take some arbitrary nonlinear function and approximate it with a linear function or a quadratic function. Right? And so the idea behind this thing called iterative LQR is going to be that you take your nonlinear dynamics or your nonlinear cost, and then you approximate it as a linear function or a quadratic. So you remember how we talked about this idea called EKFs, maybe? No, I think we actually skipped that lecture, but it's the same idea where you say, you can use the same idea for filtering. Not everything in the world is a Kalman filter, but you can convert things into Kalman filtering by using the same Taylor expansion. So all we're going to do is we're going to take this nonlinear function, we're going to convert it to an approximate linear function, take that nonlinear or non-quadratic cost function and convert it into a approximately quadratic cost. Does that make sense? Why might that be a bad idea? Or when might that be a bad idea?
It's when you want very small margins of error.
Right, when you want to make small margins of error, because the choice of approximation basically drops all of these lower order terms. And if your function is very non-linear and you approximate something that's linear, that's going to be pretty bad. Sometimes the way to fix that is if you linearize, you have to keep re-linearizing your system. If you do it at really high frequency, then you can like basically any nonlinear function can be thought of as a like composition of infinitely tiny linear functions. You just take it in, break it up into infinitesimal tiny pieces, each linear. That's the whole idea of like derivatives. And so that's going to be our whole idea. We'll work through one example. We're not going to go through the like nitty-gritty details of iLQR, but the intuitive idea is convert a nonlinear system into a linear system and a quadratic system. And you have to like keep reapproximating the function. So the important thing to remember is that when you have a Taylor approximation, it's around some point, right? So you choose some point to make your Taylor approximation around, and that approximation gets worse as you go further from that point. And so you can't just like have one approximation, you have to like keep remaking your approximation. Does that make sense?
You can just keep adjusting your point, basically.
Yeah, you keep it as. Okay, so we're just going to do a pineapple pen. We're going to combine Taylor series and LQR, right? And that's all that iLQR is going to be. So we're going to try and work through the steps one by one and try to derive approximately how to get through iLQR, but I'll leave the like details for extra credit or something. Okay, so let's study a simple case where you have a system where you have some states xt and some actions ut, and let's say there was like an optimal trajectory you're trying to follow, yeah? And so you have like xt star from where t goes from 1 to capital T, and there exists some actions that like take you from xt star to xt plus 1 star. Right? That you can just like solve for the inverse of f, that'll give you some actions that take you to the next optimal state. And so the definition we're going to have is that there will exist some u0 stars and some xt stars that represent the trajectory you're trying to track, right? And what you want to do now is you want to like minimize your cost function subject to some nonlinear dynamics, right? So for now, we'll just like, let's only deal with nonlinear dynamics. Let's not worry about nonlinear cost or non-quadratic cost. Let's just say the cost was quadratic, but the dynamics were nonlinear, okay? So your optimal control problem is going to be, you have quadratic cost, but you have nonlinear dynamics, yes? So it's trying to get, it's trying to say that from xt, you're trying to get close to xt star, in ut, you're trying to get close to ut star, right? And the cost is minimized when xt is equal to xt star and ut is equal to ut star, and the system is subject to nonlinear dynamics f, right? And you're trying to find the feedback controller, which you can apply to get these actions, right? And so what you're going to do here is you're just going to use a Taylor approximation. So you're just going to say your nonlinear dynamics, xt plus 1 equal to f of xt ut, you're going to take the Taylor approximation around xt star ut star, right? So you can say this is like we had f of x is equal to f of a plus f prime a times x minus a plus whatever, right? When you have a multivariate case, the Taylor approximation, you have to do it on both variables, right? So you have to say, let's say you have f of x comma y. You can say this is f of a comma b plus the derivative of f with respect to x times x minus a plus the derivative of f with respect to y of y minus b, right? That's the multivariate Taylor expansion. And so all we're going to do is we're going to apply the multivariate Taylor expansion around xt star ut star. You can actually choose whatever x and u you want to do it around. It's just the approximation gets better or worse. And so you're going to choose it around here. And we are next going to think of this as now a linear system again, right? So we can think of this equation or this function as your A, and think of this function as your B, right? So just to think of the matrix sizes here, this is something that maps from x to xt plus 1. So it's going to be an n by n matrix. Yes, because f is a vector valued function, right? And you're going to take the derivative with respect to a vector. So it's going to give you an n by n matrix. So if you have a, like, you remember how Jacobians work? Jacobians are when you have a vector valued function and you take the derivative with respect to a vector, the derivative is a matrix. Okay? So you have an n-dimensional thing, and you're going to take the derivative with respect to an n-dimensional thing, which means that the derivative is going to be an n by n matrix. Similarly, for the derivative with respect to action, you have an n-dimensional thing, and you're going to take the derivative with respect to an m-dimensional action. So you're going to have an n by m matrix. Yeah. So your A is going to be, your A is going to be n by n, and your B is going to be n by m, right? And this, if you remember how we did LQR, this is essentially an LQR problem, right? Because it's linear in X and linear in U, right? But it's approximately linear. Does that make sense? So all we did here is we took our nonlinear dynamics, right? And we just chose a point, xt star, ut star to like do the Taylor approximation around. And then now it's a linear function, right? So it's like linear with AT and BT, right? And so now in terms of, in terms of your like LQR equation, you can rewrite this as xt plus 1. Let's move this over to the other side, right? And now you can rewrite this as xt plus 1 minus xt plus 1 star is AT, which is this matrix, times xt minus xt star plus BT times ut minus ut star, right? And now you do a little more rearrangement, and you can write, let's call like this value zt plus 1. Let's call this value zt. Let's call this value vt, right? It becomes literally the LQR equation. Zt plus 1 is equal to AZT plus BVT, right? So it's like, and your cost function at that point is ZT transpose QZT plus VT transpose RVT, right? And so you're back at exactly the LQR equation, and you can just solve that with the same equations. Everyone follow me? So just to recap what we did, we had a nonlinear system. We had a nonlinear system F, right? And we said, we're going to take our nonlinear system, we're going to linearize it around some point. That point is going to give me an A matrix and a B matrix. I'm going to recast this as an LQR problem. I'm going to solve the LQR problem. It'll give me some set of controllers. Right? Now, what is the problem if I just did this one time? What might go wrong? Yeah. May have approximated incorrect. Right? So what the reason for iterative LQR is that what you're going to do is you're going to run this once. Around your current trajectory, you're going to execute a trajectory, you might be somewhere else, and then you'll do it again. Right? So you're going to keep doing it over and over. So you're going to iteratively linearize your system so that it's not stuck to the current approximation. You can keep redoing the approximation. So there's a huge body of literature on iLQR. I don't want to get too much into the details, but if we want to apply LQR to nonlinear systems, just remember you can do a Taylor expansion on the dynamics, give you linear dynamics. You can do a quadratic expansion on the cost, give you or second order Taylor expansion to give you quadratic cost. Yes? Okay, great. So that's the basic idea behind LQR, right? And so kind of iteratively, it looks something like this. You're gonna take your LQR, you're gonna take your nonlinear optimal control problem. You're gonna use a Taylor expansion to convert it into an approximately linear quadratic problem. You're gonna solve it very, very quickly to get your Ks and your Ps, and then you're gonna repeat, right? So that's why it's called iterative LQR. And you're gonna do this iterative linearization around your like your latest trajectory. That makes sure the approximation is locally correct. Yes, everyone buy that? Okay. So that's the idea behind LQR. And so LQR is a useful tool because it's often really efficient as compared to algorithms like reinforcement learning and things like that. And it's like you can get everything in closed form. You don't need to do like lots of GPU sampling and so on. So it's very efficient for systems that are low on compute or embedded systems in the wild and so on. LQR is a very useful tool. Any questions about LQR before we move? Also, your classmate Raymond sent me a great note about LQR. You should watch it. I think it has lots of interesting detailed derivations. Okay, so we're going to move on from LQR to the next idea called sampling-based optimal control, right? So what have we done so far? We did bang-bang control, PID control, pure pursuit. And then we said, okay, we're on more general class of systems. And we said, okay, we'll do LQR, which is more general. So it's like linear and quadratic. And then we said, okay, we want to make LQR even more general. So we're going to use iterative linearization. Like we use iLQR, but iLQR might be a bad approximation when things are very nonlinear, right? And so we want to have a better approximation here. So that's going to be our motivation behind sampling-based optimal control. It says that when you have a system that is nonlinear and non-quadratic, we did this approximation. This approximation might be a poor local approximation, right? And there's certain things that are like, certain things are hard to linearize because you may not know the derivatives, right? So doing a Taylor approximation needs you to know derivatives. And if you don't know the derivatives, it's hard to do linearization, right? And so what that suggests is we need a solution that works for general nonlinear problems and doesn't suffer from these like approximation errors or is able to incorporate constraints, right? But nothing I've told you so far kind of like allows you to solve this, right? There's no tools that we've talked about which allow us to solve this in the control section. But there might be tools that have solved this for state estimation. So we talked about, do you remember how we did filtering? We talked about Kalman filters, and then we talked about particle filters, and we went from a very specific case to a very general case. So how do you think we can solve general optimal control problems that are nonlinear and non-quadratic? When maybe like linearization is not an option. Any ideas? You just want to solve this minimization problem. How might we solve? Just like try your stupidest thing. It's gonna be good. Just sample. That's it. Just brute force the shit out of it, right? And so all we did in Bayesian filtering is we had this fancy linear Gaussian assumption. We did Kalman filtering, this and that. It's great, but it didn't work in the non-linear, non-Gaussian case. So we went to particle filtering. What is particle filtering? It's just sampling. That's it. That's it. Say we're just going to move your particles by sampling and reweighting. And so we're going to do a simple idea, which is very similar here. So to go from things like look like LQR to something that looks like sampling, we're just going to brute force the problem. We're not going to try and write it in analytical form. We're just going to brute force to computation to minimize that objective from the right. And so the idea behind sampling-based MPC is saying we're just going to take the optimal control problem from before, right? And we're just going to brute force it. We're just going to take a bunch of samples. If you have access to that, right? What you can do is if you have access to F, you can just sample a bunch of times, see which thing is good. that's your best, right? So it's like an approximation to this minimization is try a bunch of shit, see which thing works best. That's your. Right. So the idea behind sampling-based MPC is you're going to start by sampling a set of K action trajectories of P steps in the future. So let's say you had some initial starting state X naught. You're just going to sample a bunch of random actions. And you're just going to play those random actions P steps in the future. Right? And then you're going to, by playing them P steps in the future, I mean, stick them into this function F. Right? You stick your X in your U to the function F, it gives you your next X. You stick in your next U, it gives you the next F, and next X, and U to P. Right? So you're just going to start at some state. And then you're just going to like sample a bunch of trajectories. You sample a bunch of random actions. At this state, you play U0. This state, you play U1. At this state, you play U2, and so on, right? And so you have a bunch of random trajectories. For each of them, you've played some action U, and then you get a series of states. And now you're going to do this K different times, right? So you're going to do this a bunch of different times. And then you're just going to choose the thing that has the minimum cost, right? So let's say this trajectory had the minimum cost. You're just going to choose that trajectory, and then you're going to play those actions. That's it. So it's basically brute forcing the hell out of this problem by saying, we're going to solve that minimization by sampling a bunch of U's and choosing the best one. It's like throwing darts at a dartboard and picking the best one. That's it. Okay. Does that make sense? It's like the simplest possible thing you can do. Now, why might this be a bad idea?
If the random action are now already.
Yeah, if your random actions, like if your space is large, let's say you have huge action space, if you're a humanoid, you're just wiggling your arms around, it's not going to find you the right answer, right? So definitely scaling with action dimension is tough. And similarly, scaling with horizon is tough, right? Because you have to get essentially P different steps correct. Like imagine you're trying to control a humanoid, you want it to like do a backflip. That means you need to accidentally sample P steps, which will get you the humanoid to do a backflip. Right? And so that's going to be tough. What might other issues be here? Does the algorithm make sense to everyone? Okay, so what might be wrong with the algorithm? So we had one point about action dimension not scaling well. What are other issues here? Yeah. Computation inefficient. Your K often needs to be huge, and it can be tough to do that. So, what some of the papers we'll talk about on Wednesday try to like brute force it with GPUs. But yeah, it can be tough to do that. Good point. Another thing you'll notice here is I don't have any feedback. I just find the lowest set of actions and then I just play the actions. Right. So if something unexpected happens in the world, there's nothing to recover from those. Right? And so this algorithm, as I've stated it, is like open loop focus. Yep. And so that's not great. And so we're going to look at a slightly different algorithm, right? So the issues here are your open loop controller may not be able to deal with unexpected events that show up or divergences from your optimal behavior. Your computation can be expensive, right? So if you have to do computation for the whole trajectory, it can be expensive. So instead you want to do something on the fly. Your model might be wrong, right? We've talked about the models being wrong. So if you optimize it once and you run it, your model is wrong, it may never succeed. Because if your model is wrong a little bit at the start, it's going to accumulate a lot more in the future, right? And so there's this and like a plethora of other issues which make this a terrible algorithm to run. So what we're going to do instead is a replanning algorithm. The replanning algorithm says that if you have unexpected things in the future and you don't replan, then you go and hit those unexpected things. So instead, we're going to try and run a system that doesn't just run one plan, but instead tries to do replanning, right? So it tries to say, okay, I planned once, then I'm going to execute one trajectory, and I went somewhere that I didn't exactly expect, and then I'm going to replan again from that initial trajectory, right? So it's like, I started here, I'm going to run planning to get this trajectory. I'm gonna take the first step in this plan, right? It gets me here. Not where I expect it to be, and then I'm gonna replan again. Right? And so I'm gonna rerun that whole optimization again. And that's gonna be another trajectory. I run that again, I replan again, I replan again, I replan again, right? And so the idea of MPC or model predictive control is also often called receding horizon control. Is just that you do planning, you execute one step of your plan, and then you plan again, right? And so, in effect, it basically looks something like this. You plan with random shooting or random action in the future. You choose the best thing, you execute it, and then you went somewhere else, and then you run it again, right? And so the whole point is that it's like essentially giving you feedback, and it's accounting for model error. And as a result, because you're replanning every time, the burden of optimality on your controller is lower, right? So you don't have to be perfect the first time. Because you're replanning again, you can be a little imperfect because the next time step is going to be here. Right? And so the next algorithm we're going to discuss is called model predictive control, or MPC. And the key idea behind MPC is just doing replanning. That's it. Same algorithm as one, just replan. Does that make sense? Yeah.
This seems like a very dramatic, like, derivation from the actual path itself. Like, we're talking like very small quantities of it, right? But it's not quite as dramatic.
Oh, you mean the figure?
Yeah.
Yeah, it's not that.
Okay.
Yeah, that is exaggerated. Yeah, yeah, the figure is exaggerated for dramatic effect. Yes, exactly. Okay, so the general idea behind MPC or model predictive control is that you're going to run a plan, you're going to execute the first step, you're going to run a plan, execute the first step, run a plan, execute the first step, right? Just those 3 steps. And you don't have to run sampling for your planner. You can use iLQR for your planning. You can use whatever you want for your planning. But replanning is going to buy you a bunch of stuff. Right? Replanning is going to allow you to deal with unexpected things. It's going to allow you to not have to do very, very expensive computation because you can be more suboptimal if you can replan. And it's going to allow you to deal with these accumulating model errors with your replanning. Okay, so the general schema of a replanning system is I'm going to start here, I'm going to plan, I'm going to execute something. It's going to be a little different than what I thought. And I'm going to replan again, right? I'm going to execute the next thing. I missed one. I'm going to execute again, and then I'll like repeat this over and over. Okay, very simple. So in your homework, you basically have a version of this MPC algorithm where you're going to do random shooting. You're just going to choose random actions. You're going to play them forward. You're going to see how good or bad they do. Choose the best one, execute one step, replay. Okay? It's going to be exactly the same. That makes sense? Much easier than iLQR. Okay. Now, why might this be a bad idea? I know every algorithm I say, I ask you why it's a bad idea, but it's good to know the cons of your methods. So when might this be a bad idea?
When the horizon is long, that means
Yes. It's very expensive, yes. So often what makes these methods hard is that you have to replan in real time. And if you have like a car moving at high speed and you're replanning in real time, each planning step has to be pretty efficient. And so often what people will do is like try to use things like GPU parallelization to make step 1 better, or they like are okay having a more approximate solution to step 1 because the replanning takes care of it. Okay, so does this work? Here's some videos of it working in simulation, and some from one of my colleagues at Berkeley who's trying to make this little cockroach drive around and follow this path over here. And you can see that essentially it's like going off the path at places, but it's like replanning and getting back on the path because the model here is pretty inaccurate. It's a cockroach. Cool, but a lot of systems today, like production systems, helicopters and cars and so on, use some version of MPC. They all use a different choice for, step 1 here. Most people are not doing random sampling. They're like trying to use some approximation, which is a little bit better, but a lot of them use this basic idea. Okay. One additional idea I wanted to touch on is that if you are doing random shooting, often the issue is that your actions are going to be completely random, like you just mentioned, right? So the chance of you getting a humanoid to backflip is pretty small. So instead, what you might want to do is find a better way to sample trajectories that is higher chance of success, right? And so basically the problem here is that you're like searching for a needle in a haystack. The needle is the robot backflipping, and you're searching for it by just shooting out random action to do it. And that's unlikely to succeed just because of probability. Right? It's like a random walk. And so instead of that, we're going to try and do something a little bit better. Right? So we're going to try and develop better sampling techniques for MPC. Right? So we're going to say that originally what we did was we sampled actions from some uniform distribution or a Gaussian distribution. And the chance of that succeeding is not that high. Right? But does anyone know how the cross entropy method works? You heard of the cross entropy method? The cross entropy method is basically, it's very simple. It's basically you throw a bunch of darts at a dartboard, and you see which ones got closest to the middle, and then you like refit a Gaussian around those points, and you throw darts again. And then you see which ones got, you take the top 10%, refit a Gaussian to them, throw it again, repeat, right? So it's basically do a bunch of random stuff, rank them according to how well they did, take the top 10%, refit the Gaussian, repeat, right? And so basically it's going to like keep getting you closer to something that's good because you're only taking the top 10%. Yeah. And so what we're going to do is an algorithm that looks very similar. And we're going to say that rather than just sampling uniformly, can we try and inform our sampling with a cost function, right? So rather than saying just throw random things at the dartboard, we're going to say try to use your cost function in your sampling distribution so you sample around things that you care about. And so like, who cares about the humanoid lying down? It doesn't matter. I want the humanoid to backflip, right? So I want to sample more around actions that are getting me closer to a back. That's the idea behind this next algorithm, which is called MPPI, Model Predicted Path Integral. And all that it's saying is that iteratively upweight the sampling distribution around things that are low cost. So you sample a bunch of stuff, you see which things are low cost. The next time you sample stuff, don't sample things from the uniform distribution, sample it from something centered around what is low cost. That's it. That makes sense? Right, so what this idea called MPPI is very simple. It's just saying you sample n action sequences to start. Then you are going to roll them forward using your dynamics model, the same as before, right? And what we did in the previous step was we just took the best one, executed the first action, and we're done, right? What you're going to do in MPPI is you're going to weight. You can think of this term as a weighting function, but you're going to weight every trajectory by its exponential of negative cost, right? So basically things that have really low cost are going to have really high weight. Things that have high cost are going to have low weight, right? And you're going to reweight your action distribution by averaging actions weighted by exponential negative cost, right? So imagine there were some trajectories that had really high cost, they're like really low weight, and some trajectories that have low cost, that have high weight. And so your action distribution is going to move towards things that have low cost, right? And then you're just going to repeat. And so the point is that at any step, what MPPI will do is that it like samples a bunch of random actions, rolls them forward, weights them according to the exponential negative cost. And then now you have a new sampling distribution. You go and repeat your sampling process. And now this PU is more targeted towards things that are good. So you're not wasting samples on things that are not good. Right? And so it's just like focusing your sampling towards things that matter. You went by that? Any questions? Okay, so the cool thing about MPPI is that it really works. So here's some but this is like actually the learning model. But just trying to get it to so very successful. And then he took that and then he developed this, which I think is much cooler. But they're trying to get cars to drive around these uneven terrains in the middle of Ellensburg. And so they have these cars which have some approximate model of the world, which is going to be very wrong. And they're going to keep updating it so that they can go at high speed up and down these hills and across ditches and in the water. Yeah. It's very robust to real world deployment. And the key is just replanning. You just have to keep replanning. Yeah, I think this is awesome. I mean, it's quite scary to be the driver, but cool. So that is sampling based optimal. How do we feel about that? Relatively easy compared to the rest. Yeah. Okay. So one of our papers is going to be on PID control, and the other one is going to be on sampling based optimal control. And I have 10 minutes or so. Let's see if we can get through Lyapunov. I think it's super cool, but we might have to skip some of the derivations to make sure we fit it in there. Yeah. But the idea behind Lyapunov theory is that we want to get controllers that are guaranteed to be stable, right? And so stability essentially just means that as time goes to infinity, your error is guaranteed to converge to zero, right? So a stable system is one where the error is always guaranteed to converge to zero under the model of your system, but not every controller is a stable controller, right? So if you have a pendulum or something, if you have the wrong controller, it can become unstable. It's not guaranteed to converge. And so the idea behind Lyapunov stability is, can we take controllers and can we certify that they're going to go to zero? So if I have like a helicopter and I can guarantee that it's going to get to where I want, then I'm much more likely to trust it, right? So what Lyapunov theory tries to do, it tries to provide certificates for controllers, which says that your controller is going to take the error to zero, right? The caveat is, it doesn't tell me what time it's going to take it to zero. It says that it's at infinity, but at least you have a guarantee that the system is going to converge. Right, so the idea behind Lyapunov theory is just to guarantee stability. So let's try and look at, a simple system like a pendulum. Right, so pendulum is just something that is swinging like that. You can apply actions at the same hinge. If you remember last lecture, we had an inverted pendulum. Now let's just take a non-inverted pendulum, right? And we can apply actions, has gravity, there's a mass at the end, right? And so the equations of motion are going to look something like this. It's basically the same as we derived last time. Not that different. And so it's going to say ml squared times the angular acceleration plus mgl sine theta is equal to the action. Right? It's like basically the same derivation as we had last time. And the question we're going to ask in Lyapunov stability is, how do we choose u? How do we choose our controller such that at convergence theta goes to zero and theta dot goes to zero? Right? What does theta goes to zero and theta dot goes to zero? It means that the pendulum comes to rest in the middle, like velocity is zero, position is zero, right? And the question is, how do we choose our u so that this is guaranteed to happen? Okay, so the simplest thing you can think of is, let me like not put any actions. Let me set u to zero. Now, do we think that this pendulum is guaranteed? Like in most realistic pendulums in the world, you're going to have damping, right? So you're going to have friction. And so most pendulums will converge, but in our system, there's no friction. There's no damping, right? So if you have a frictionless pendulum, it's just going to keep swinging around. There's no reason they'll ever converge, right? And so a passive pendulum is not stable. And what we're going to try and do is we're going to try and design a controller, which is going to make the pendulum stable. And once we do that, we can come back and make our car stable. Right? But we're just going to take a detour with the pendulum because it's easy. Okay, so to recap what the point of Lyapunov stability is, we want to drive our error to zero. We've seen that in the pendulum, if you set u to zero, it's not stable. The theta doesn't go to zero, theta dot does not go to zero, right? It just keeps swinging. Okay, so we are going to try and design a controller which sends theta dot and theta to zero at convergence, okay? And so we're going to try and choose this controller where u is equal to minus k theta dot, which means that the action u is minus k times your velocity. Intuitively, this means that you just want to, it's like a PID controller, right? Saying that your action is opposing the velocity scaled by some factor. And so if I'm moving fast that way, my action is going to move that way. Moving fast that way, my action is going to move. Right? So intuitively, this feels like could help, but how do we guarantee that this is stable, right? I want to guarantee that this thing is going to take me to zero. So what is the simplest thing I can do to guarantee this? Yeah. Sorry.
three plans, basically like lower the standard.
So that's more of an algorithm, but I want to guarantee that it's always going to go to zero. So I want like a theoretical guarantee. So the simplest thing you can do is just, try it a bunch of times, right? Take your system, use this control law, run it like 5 million times, and see how it like converge all the time. But the problem with that is that, okay, pendulum is a 1D system. Imagine I had a 100D system. I can't cover everything. And so what I really want is a way to guarantee that the system is going to converge without having to try everything. Right? So the point of Lyapunov stability is that I want to show that a system will converge without trying everything. Right? So oftentimes in robotics, the answer is just try it and hope that it works. The good thing about Lyapunov is that it like guarantees that it'll work in certain systems. Okay. So the key idea behind Lyapunov theories is just think about it like an energy in a system, right? If you have a physical system, a Lyapunov function is the same as an energy. And so the idea behind Lyapunov stability is that if you can show that the energy of the system, energy is always positive, right? And if you can show that the energy of a system will go to zero, then you know that the system has come to rest, because the energy of the system is zero at rest. And so if you can describe the energy of a system and show that the energy of the system goes to zero, right, with time, then you know that the system must come to rest. That's the whole idea behind Lyapunov stability. It's just saying, try to define the energy and show that the energy is always decreasing and it's always positive. So if you can show the energy is always positive and the energy is always decreasing, then just by sandwich theorem, it has to go to zero, right? Like, a positive thing that's always decreasing, where is it going to go? It has to go to zero. Right? So that's the whole idea. And so you're going to define the energy of this pendulum, right? The first term is kinetic energy. The second term is potential energy, right? And you can see that it's positive, right? The first term has a squared, it's ml squared theta dot squared. And the second term has a 1 minus cosine theta, which is always positive, right? So both terms are positive, which means the whole thing is positive. Right, so the energy is always positive. And if you derive the derivative of the energy, when you plug in, so if you, I'm not going to work through this fact, but basically the derivative of the energy comes out to be theta dot times u. And if you plug in your controller, u is equal to minus k theta, then your derivative of your energy is minus k theta dot squared. Yes? Just take this thing, plug in u is equal to minus k theta dot, you get minus k theta dot squared. And minus k theta dot squared is always negative, right? Because theta dot squared is always positive, which means that minus k theta dot squared is always negative. So what does this mean? You have a positive energy, the energy is always decreasing, so the energy has to converge to zero. And the only place where that thing is zero is when theta is equal to zero, and theta dot is equal to zero. Like, look at that energy up there. The only place it's going to be equal to zero is when cosine theta is equal to 1 and theta dot is equal to 0. Right? And so what that guarantees is if you can show that this controller has positive energy and the energy decreases, then it'll converge to 0. Right? And so all that the Lyapunov function is a generalization of energy. So it's saying that this was literally energy, but you don't have to pick energy. You can do it for any function. You can choose any function if you can show that function is positive and that function is decreasing with the system, right? So if you can show the function is decreasing and positive, it has to go to 0. Right, so that's the whole idea of Lyapunov theory. I think we have like a minute left, so I won't go into the details. But the point here is that what Lyapunov theory allows you to do is that if you know the dynamics of your system and you can find this Lyapunov function allows you to guarantee that your system will converge, right? And so if you can guarantee that your system will converge, you have some trust. And AI is all about trust. And so the whole point of Lyapunov theory is, one, you can use it to construct stable controllers. You can use it to design controllers that are guaranteed to converge. And two is if someone gives you a controller, you can try and verify that it's stable without having to like sample all of it. And so you can provide a guarantee rather than like having some chance you miss something. Okay. I'll try to see if I can cover the remaining. I think the math of it is cool, but hopefully that makes sense. Cool. All right. Thank you all. See you on Wednesday.